Okay, so we finally reached the point in calculus where we are completely done with derivatives, and now we're going to head into pretty much the third branch, which is integration. And this is the introduction to it. So, when it comes to integration, and I kind of talk about it over here, in calculus, the result of that, it represents, I don't know why I put the word that, but essentially this over here, this integral symbol represents the antiderivative. Right? So before, when we went from f of x to f prime of x, right? In order to get there, we took the derivative. Well, now, if we basically want to do the reverse of that and go from f of prime of x to f of x, to get from there to there, we are going to integrate. All right? And as you'll find out soon, there's going to be a series of rules, a series of process, it's a whole new branch, like I said. So one of the things that you have to understand, or most of you who have taken calculus before, whenever you're taking the integral of something, you're essentially finding the area under the curve. All right. So let me just kind of give you just a very quick, simplistic, elementary example of what we're even talking about. So it says, let's say a car travels at a constant speed of 50 miles per hour. How far did the car travel after 4 hours? Well, if you think about this, if it's going at a constant speed of 50 miles per hour, well, the graph is just going to look like a constant line or a horizontal line going at 50 miles per hour. I didn't really label my axes, but that's what this means. So you're going at 50 miles per hour, and we want to know how far did the car travel after 4 hours. So I'm going to stop it right there at 4. Okay, so throughout this time, the car has traveled some amount, some distance, right? But, and if we were to answer this, like even if we didn't have a graphical display of this, most of us would just kind of remember how to do this and say, well, 50 miles per hour, if we did unit conversions, kind of like in chemistry, 50 miles per hour times 4 hours, well, the hours cancel, you multiply across, and you have 200 miles, right? This is how we would normally answer the question. But in calculus, when we think about a question like this, we kind of want to think about what is the area, think of it in terms of like, what is the area under this curve, right? So it went 50 miles per hour horizontally, and then it had a height of, the height is 50 miles per hour, and then the width of this rectangle is 4. And so the area underneath this curve is 50 times 4, and we get 200, right? 200 miles, right? And that's kind of the whole idea of what we're trying to accomplish when we're integrating. Now, obviously, rectangles, we know that's just the base times the height. But then when we start getting into curves, that's where things start to get a little bit more complicated. All right, so this is why we have the concept of Riemann sums. Calculating a Riemann sum, it's not the most accurate way, but it's a way to estimate the area under the curve. And this is kind of the way that, or traditionally, this is how most calculus classes start integration. Because integration, and, I'm sorry for those of you who know all of the integration rules, but, we kind of have to start off with Riemann sums. But integration is, finding the area under the curve between 2 points. And Riemann sums is what we're going to do is we're going to just kind of draw geometric figures underneath the curve, find the areas of each of those geometric figures, add them up, and then we pretty much get like a rough estimate of what it is. All right, so let's kind of see what are the 4 types of Riemann sums that we will see. So it says we are going to use the function f of x equals x squared plus 1 as an example and estimate the area under the curve from 1 to 3. I wish I would have typed my notes a little bit better, but typically what they would do is they would tell you how many sub-intervals they want. So we'll just say using 4 sub-intervals. Okay, so so these are the 4: left hand sums, right hand sums, midpoint sums, trapezoidal sums. And with these first 3, we're pretty much using rectangles. Okay. Because, we all like rectangles. We all know how to find the area of rectangles, and, they're easy to draw and easy to calculate. All right. You'll find out that this chapter is very tedious, but I've seen it before. I've seen a lot of AP exam questions that ask this type of concept, so we got to kind of understand it. So if they want to know what is the area of this curve from 1 to 3, right? Well, we have this area right here. So ultimately what we're trying to do is we want to know what is the area from here to there. All right, this entire area underneath the curve. And we're going to do that using all of the 4 different processes. But the thing is, we don't necessarily, not yet at least, we don't necessarily know how to find this area. So the whole point of this is what we're going to do is we're going to draw like rectangles, and we want 4 subintervals. So we're going to draw 4 rectangles, right? And then we're going to just try to, just draw them and then calculate the area of those rectangles and then figure it out. So I think, for the sake of this video, I don't want to sit here and draw these rectangles, and take a lot of time. So I'm going to go ahead and show you like these rectangles that I've already drawn. All right. So what you'll notice here with my left-hand sums, right, I went ahead and I have 4 rectangles. I have 4 rectangles like this. These are kind of like underneath the curve, and these are a bit above the curve. But the whole point of like left-hand Riemann sums is we're looking at these 4 rectangles, and the main difference between that is we have, 1, 1.5, 2. So let me just write that out, 2, 2.5, and 3. So here we can create, these are pretty much our intervals for 4 rectangles. But the main difference between left-hand sums and right-hand sums is what we're doing is with the left-hand sums, we're looking at the first 4 numbers, right? And kind of drawing rectangles like starting on the left-hand side of this interval. So I'm going to draw a rectangle up until my function, and then draw a little rectangle. From here, I'm going to go up into my function, draw a little rectangle, up until my function, draw a little rectangle, and so on and so forth, right? And what you'll notice is here you have 4 rectangles, and then when we calculate the area of these 4 rectangles, we're going to add them up and get some kind of area, right? But the problem with this is, this isn't like the perfect estimation. And the reason for that is because look at all this extra area that we have, right? That's not even accounted for, right? I mean, again, that's why we say that this is an estimate. But this over here, because we're missing so much area underneath this curve that's not taken into account, that's why we call this one an underestimate, right? Now, on the other hand, if we have right-hand Riemann sums, we're kind of, we have the 1, 1.5, 2, 2.5, and 3. We're actually using the upper bound of the intervals, right? So we're looking at from 3, 2.5, 2, and so on and so forth. And we're going from 3, going up to our function, creating a rectangle. From 2.5, going up to our function, creating a rectangle, so and all of that. Now, over here, we have extra. Now, we're actually calculating for extra area above the curve, right? That is kind of unnecessary. We really only need to know the area underneath the curve, but we have all this extra area. That's why we consider this an overestimation. All right. And the concept of Riemann sums is really simple. Draw rectangles, find the base and height of each of the rectangles, add them up, and there's your estimate of an area, right? So, but yeah, that's part of the main issue that I notice with students when they're solving these things. The way I answer these questions is I say, okay, well, if I have to do from 1 to 3 and I were to create 4 rectangles, I usually end up with 5 numbers in my interval. Right-hand Riemann sums, I just look at the last 4. Left-hand Riemann sums, I look at the first 4. And then I use that to kind of calculate the height of those rectangles. All right. Then we have midpoint sums. All right. So this is a much better, estimation of the type of this is a much better estimation of the area underneath this curve, because if you think about it, so what we're doing is we're creating this still 4 rectangles, but here we have our interval 1.5 and 2.5. But the thing is, what we're essentially doing is we're going to create these rectangles. We're going in between 1 and 1.5, and then kind of drawing a rectangle where the middle of that rectangle crosses the curve. Same thing over here. The middle of this rectangle is what crosses the curve. The middle of this rectangle is what crosses the curve, so on and so forth, right? So essentially what's happening here is I'm creating these rectangles, and this, we can't really tell right off the bat if it's an over or an underestimation, but you'll notice that like for this missing area that we are not taking into account for here, we're kind of making up for it by calculating this little area there. for this missing area it's being taken accounted for by this little area here, and so on and so forth. Is it still a perfect estimate? No, not necessarily. Then we have trapezoidal sums. So it's kind of hard to tell here. It does look like I just drew lines, but I did draw trapezoids here. So I have, we're not dealing with rectangles anymore. We're, as the name suggests, we're working with trapezoids. If I kind of go up with the curve like that, and I create a trapezoid, right? I can create 4 trapezoids, and this, for generally speaking, usually does give you the best estimate of the curve. You could just visually see that it does a good job of doing that, or of estimating that, and because these areas are going to be very close to what that area is under the curve. Sometimes you go a little bit above, sometimes you go a little bit below, but for the most part, it's pretty good. The other thing that's worth noting too is that the width of your intervals. Obviously, these rectangles would do a good job of that. But imagine if I were to, and let me go back to like this one. Imagine if I were to just use 2 rectangles to calculate this area. And let me use the right-hand sums. So 2 rectangles, I'm using the last, for right-hand, I'm using these 2. So if I were to create a rectangle here and draw that, and then draw another rectangle here. So that's gonna be a much worse estimate than if I used smaller rectangles, right? Because now I have all of this area that's just, completely overestimating what's going on here. However, the smaller the rectangles that I use, the more area it fills in underneath that curve, and the better my estimate is going to be. I wish I had technology to kind of show this to you, but you'll notice that if I, these were supposed to be overestimations, my bad. But anyways, you'll just, that's just something else to keep into mind, and this is something that's going to help us with integration later. The bigger the intervals of your rectangle, the smaller the intervals of your rectangle, the smaller the intervals of your rectangles, the better estimate you're going to be. And you'll see later on that whenever we do an integral, dx, that's like an infinitesimally small width of your interval. But again, we don't need to know that just yet. So let's just kind of move on to the next page. If I can find my next page. Here we go. So now let's get into the actual calculations of the 4 types of Riemann sums. All right. So as far as the calculations of these Riemann sums, what we're going to do is we're going to use the same function, right? But this time we're going to actually calculate, and I decided to do the calculate from 0 to 3 using n equals 6. All right. So here's what we're going to do. What we're going to do is we're going to have 6 intervals, and then we want to know the area of this curve from 0 to 3. And we're going to find the area underneath that curve, and we're going to use rectangles for the first 3 and trapezoids for the last one. This last one with the trapezoids, it's a pain in the butt. But, and like I said, this whole chapter is a pain in the butt, but we just kind of have to get through it. So the best way of figuring out the width of your rectangles, you can kind of intuitively sit there and kind of think about it, but the nice little formula they want you to use is b minus a over n, right? That'll tell you the width of the rectangle. So our interval is from 0 to 3, so it's going to be 3 minus 0 over the number of subintervals that they want, 6, which is 1/2 or 0.5. All right, so that's going to be our intervals for here. So we're only going up until 3. So we're going from, so if we have to go up 0.5, so from 0 to 0.5, 1 to 1.5, and 2 to 2.5. All right, and of course, don't forget 3. All right, so if we want to do left-hand sums, what we're going to do is we're going to create rectangles with the left-hand bounds of the intervals, right? So if we're doing 6 rectangles, we're going to look at the 6 numbers on the left, right? So we're going to create a rectangle here that has that width, another rectangle here that goes that far, another rectangle here that goes as far as halfway through, this rectangle that goes that far, this rectangle that goes that far, and this rectangle that goes that far. All right. So those are the 6 rectangles that we're going to end up using. Now, obviously now what we're going to do is we're going to calculate the width of these rectangles. So the width of these rectangles they're all going to be 0.5, and that's what you'll find out. All the widths are the same. So and I meant to say earlier that we're going to find the area of these rectangles. So if I want to know the area of this first rectangle, well, I know that the width is 0.5, right, or 1/2. I'll use 1/2 in the formula, but it's going to be 1/2. But the height of the rectangle is kind of dictated by whatever our function is. If I plug in 0 into my function, well, my height is 1. So it's going to be, from when I plug in 0, where that's located on the y-axis or at that function, that's going to be the height. So I'm just going to say multiply it by f of 0, just to kind of keep it general. All right. Then what I'm going to do is I'm going to add the area of this rectangle. So the width is 1/2. And then the height is going to be whatever we plugged in for 0.5, so f of 0.5. And again, you can plug that into your calculator and figure it out. Now for this rectangle, the width is 1/2 again, so 1/2. And then the height is going to be, I mean, it looks like 2, but, you know, you have to think about if I plug in 1 into that. But yeah, it is 2. But we'll just say f of 1 to keep it general. Plus, I mean, hopefully you guys see the pattern here, plus 1/2 times the height of this rectangle is f of 1.5, plus 1/2. Height of this rectangle is f of 2, plus 1/2. The height of this rectangle is f of 2.5. All right. So, unfortunately, as I'm making this video, I do not have my calculator with me. And there is a much faster way, or there's a very fast way of doing this on your calculator with lists inside of, like, you know, from what I learned in statistics. But you know what? I'll probably get back to that in a second. For now, I'm just going to kind of get these set up. But that's essentially what we have here. So I'll show you how to do this on a calculator maybe in a second video. And it'll be a really fast and easy way of calculating all of these things. But I put all of this in my calculator, and after doing all that work, I did get 9.875. Okay? So, that's what I get for being unprepared for making this video. But anyways, so now we're going to do right-hand sum. So again, it's from 0 to 3. My little sub intervals are going to be from 0 to 0.5, 1, 1.5 to 2.5. All right. But now what we're going to do, when we're talking about right-hand Riemann sums, we're going to create rectangles on pretty much the right-hand side or the right-hand intervals, right? So I'm going to start with 3, and I'm going to draw my rectangle there. Halfway through, go down. From here, at 2.5, go from here. Halfway through, go down. From here, halfway through, go down. And then now my next rectangle is down here. Halfway through, go down. Here. There we go. Horribly drawn rectangles, but whatever, it'll do. So now the the width of these the height of these rectangles is dictated by plugging in the values from here to here, right? So I guess if I'm starting right now, I'll just start at the right-hand-most rectangle. So it's going to be the width of the rectangle is still going to be 1/2, and then the height of this one is f of 3 plus 1/2 f of 2.5. I don't know why I put extra parentheses. Plus 1/2 f of 2. That's the height of that rectangle. Plus 1/2. Feel free to skip through all of this if you understand what's going on. I'm just writing it because I have to make this video. Anyway, so plus 1/2 f of 0.5. All right. So again, there's a very fast way of doing this on your calculator. Unfortunately, I don't have it with me. But if you want to sit there and actually punch all of this in your calculator and calculate that, then that's fine. And you should have gotten 4.735. All right. So there you go. And you'll see this right here, that should be an overestimation because we have all of this area that we calculated that's not necessarily part of the area underneath the curve. Over here, this is definitely an underestimation because we have all of this missing area that we're not even taking into account when we're doing the area of our rectangles. Now we get to the annoying ones, which is the midpoint and trapezoidal sums. So if I wanted to calculate these guys, let's see, I have we're still doing from 0 to 3, right? And we're still using 6 subintervals, and the width of these rectangles are still 0.5. But so what I'm going to do, I'm going to draw a little tick mark, so we're still doing 6 rectangles. So the thing is, if I'm trying to do the midpoint, I'm essentially, like, the intervals that I'm using, I'm going to use the midpoint, like the midpoints of these rectangles. So let me kind of draw just longer lines to represent these individual rectangles. So these are kind of the 6 rectangles that we're going to use, but we're going to use the midpoint or go halfway in between those rectangles, and those are going to be, you know, the height of our rectangle. So the middle of this rectangle is here, so it's going to go kind of like that. The middle of this rectangle is like right here roughly, so it's going to kind of look like that. Middle of this rectangle is like right there somewhat. Right? The middle of this rectangle is about up here. I'm kind of rough sketching this, but it's coming out all right. Middle of this rectangle is like here probably. There you go. Right? Which is a much better estimate because you have, even though you're not taking this area into account, you're kind of making up for it by overestimating this little area. But the main difference that you have to understand here is that we're going from between these. Like originally it was 0.5, 1, 1.5. Those were like the intervals of your that told me where the rectangles are, where the upper endpoints and lower endpoints of the rectangles are. But if we're going in the middle, halfway between 0 and 0.5 is 0.25. Halfway between 0.5 and 1 is 0.75. Halfway between these two is 1.25. I'm going to draw little arrows because it's kind of hard to see. Halfway between 1.5 and 2 is 1.75. The halfway mark between these two is 2.25. And the halfway mark between these two is 2.75. You weren't even seeing that. I'm sorry. But yeah, the halfway point is 0.25, 0.75, 1.25, and so on and so forth. So the height of this rectangle is determined if you plug in 2.75 inside of your function. So those are going to be the 6 rectangles here. So it's 1/2 f of 0.25 plus 1/2 f of 0.75 plus 1/2 times f of 1.25 plus 1/2 f of 1.75 plus 1/2 f of 2.25 plus 1/2 of f of 2.75. There's my extra parentheses for some reason again. All right. Now, if you calculate all of that, you should have gotten 11.9375. So I think this is getting pretty close to what that real area is under the curve. Here we went a little bit overboard. Here we fell a little bit short. All right, but now let's kind of see what the trapezoidal sums kind of look like. Now, hopefully you guys remember from geometry what the area of a trapezoid is. So if you don't, that's fine. The formula for the area of a trapezoid is 1/2 times base 1 plus base 2 times the height. So if I had like a trapezoid, right here you would have base 1, base 2, or the length of base 1, the length of base 2. Here you have a height, and you have to just you add those two together, times it by the height, and then divide everything by 2. And that's essentially what we're going to do when we're creating these trapezoids. So just to kind of show you guys what that looks like. So obviously 6 subintervals again, from 0, 0.5, 1.5, 2.5, and all of those. Essentially, to create the trapezoids, I'll use this one because it's easier to see visually. So here's like base 1, and then base 2 will essentially be that. And then we just kind of connect those two, and there you go. You have a trapezoid. So base 1 is essentially f of 3. Base 2 is essentially f of 2.5. And then that'll tell you the lengths. The height of this trapezoid is, it's kind of like an upright vertical. Well, a vertical trapezoid kind of with the slanted up there, right? Or with the diagonal up there. So then the width of that is going to be considered like our height. And then 1/2 we just always include into the area of a trapezoid. And then This next trapezoid, well, that's going to be f of 2.5 and f of 2 for the, the lengths of the base 1 and base 2, right? And then you have that trapezoid. So, I'm just going to draw lines on all of these, and then, all right, and I'm going to shorthand this one. I don't want to sit here and write out the formula for all of it, but essentially, let's just kind of look at this trapezoid first. This trapezoid, the base 1 is f of 0. Base 2 is f of 0.5, right? And again, as we have to follow the formula, so it's 1/2 times that, times base 1 plus base 2 times the height, and our height of this trapezoid is 1/2 again, right? So then we're going to do the next trapezoid plus 1/2. You can see how this is getting annoying, right? But I hope they don't ask too many of these on the AP exam. But anyway, so it's going to be 1/2, and then base 1 is f of 0.5 plus base 2 is f of 1. And then the width of that, well, not the width, the height of that trapezoid is 1/2 again. And let's just pretend I wrote it all out for all of those, and let's go to the last trapezoid. So doing the same thing, but then the last trapezoid is 1/2 times the length of base 1 is f of 2.5. The length of base 2 is f of 3. So those two added together. And then times the height of that trapezoid is 1/2. All right. So through the magic of video, and I've already done all of this. If you calculate all of this, you get 12.125, which again is pretty close to, both of these are pretty good estimates. All right. Now, again, I wish I had the calculator, but I do remember what the function input is. If you wanted to do all of this in your calculator and integrate with the calculator, and we're going to do that more in the next section, let's just kind of figure out what the actual answer is. So what you're going to do when you go into your calculator, luckily I remember, you go to math, and then underneath math, you just kind of scroll down. You scroll down all the way to where it says fn int, right? Basically the integral function on the calculator. And some calculators are a lot more fancy and actually set up the integral for you. Like I think some of them even set up the integral like from a to b, and then you type in your function there, and then it's dx, where I think you have to put in with respect to x. My calculator is an old school one, so I have to do f of n, and then I have to type in my function. So it's x squared plus 1. And then after that, you have to put comma with respect to x, comma, and then you put in your bounds that you're interested in finding the area under from 0 to 3. And your calculator will actually calculate that to be 12. All right. There is definitely a way of doing all of this by hand with rules, and most of you, I think in BC, most of you know how to do that already. But that's a good way of checking how to do it on the calculator. And as you can see, 12 is the real area, and believe it or not, this one was actually the closest one to it, the midpoint one. That's surprising, but yeah, it worked out nicely. So as you can see, if 12 is the answer, here we have an overestimation, here we have an underestimation, and that's about that. So that's kind of the general overview of Riemann sums. I'm trying to see what did the last page look like. This stuff I would like for you guys to do on your own, and here's kind of a real life application of all of that. And I think I'm gonna have to make another video with of how to calculate all of these things with your calculator. Maybe I'll do that during like third period or something, because I'm always recording during class. But yeah, so these I would like you to try to do on your own. And I'm going to post the solutions online. And here I want like kind of a real life application of what all of this stuff is. So of course, try to do this on your own, try to understand it. And if you have any questions, you are always free to ask me or talk to each other. Take care.